Hello students, thank you for subscribing to my channel. Today we will continue talking about IB Physics data booklet. We will discuss equations, and to start working with this video you should have this booklet, IB Physics data booklet, pen and notebook. I can wait for you. Just take pen, notebook and IB Physics data booklet. I wait. Ready? Let's start. So IB Physics data booklet, equations, discussion, page 5. So open page 5. Here we see subtopic 3.1 thermal concepts. Q is thermal energy released or absorbed during the process. So processes in which temperature changes: heating and cooling. In heating Q is positive, in cooling Q is negative. M is mass, C is characteristic of material, specific heat capacity of material, and delta T is temperature change. So here temperature is changing. In some processes take place at fixed temperatures called fixed points: melting, boiling, thermal energy is absorbed; freezing, condensation, energy is released. And formula for energy is mass multiplied by characteristic of material, which is called specific latent heat of material. Notes: Kelvin temperature is by 273 degrees greater than degrees Celsius. Definitions: heat capacity of an object is energy required to change temperature by 1 degree. This is why we divide energy by delta T. Specific heat capacity of material, small c, is energy per 1 kilogram per 1 degree Celsius. And specific latent heat of vaporization or boiling is energy per kilogram. Subtopic 3.2 modeling a gas. One of important characteristics is pressure. General definition of pressure: pressure equals force over area. Amount of gas can be expressed in terms of moles. 1 mole contains n Avogadro, which is constant, molecules. This is why number of moles is total number of molecules divided by n Avogadro, small n. Here we see very important ideal gas equation, which has pressure, volume and Kelvin temperature of the gas. R is gas constant and n is number of moles. Another important formula is average kinetic energy of one molecule. It is 3.2 times Boltzmann constant times Kelvin temperature, or instead of Boltzmann constant we can use gas constant divided by another constant, Avogadro number. Plus, to gas equation, it is useful to know what happens when one of the quantities is constant. For example, when temperature is constant, pressure, volume are inversely proportional and their product is constant, doesn't change. When pressure is constant, volume and temperature are directly proportional, their ratio is constant. At constant volume, ratio of pressure and temperature is constant. Also, you should know what means percentage difference. So if one quantity changed from x1 to x2, percentage difference is change divided by the value multiplied by 100. If you want to know total internal energy of an ideal gas, you should multiply number of molecules by energy of one molecule. You will get interesting formula 3.2 nRT, number of moles. and gas constant. Subtopic 4.1 Oscillations. In oscillations we have repeated motions. These motions have time during which it happens. It's called period, and how many times it happens? Every second. It is frequency. This is equation linking period and frequency. Here I give you definition. Period of oscillation is time of one complete oscillation. This is why you divide. If you measure the time of n oscillations, complete oscillations, you divide time by n, you get time of one complete oscillation. Frequency is vice versa. It is number of oscillations per 1 second. Another characteristic is called phase difference. If you have shift in time, so for example one oscillation happened, another is shifted by delta t, then the phase difference will be 2 pi over t delta t. Or in terms of degrees, so this will be in radians, this will be in degrees. Traveling wave. So for traveling wave we have wave equation which links speed, letter c, for wave, equals frequency of wave multiplied by wavelength. What is wavelength? Wavelength is distance between two closed maximums, troughs, or minimums, or points in phase. Wave characteristics. Intensity of wave proportional to square of amplitude, inversely proportional to square of distance from the point, from the source, and if you have polaroid, depends on cosine square angle of between line of polarizer and electric field of the light. Useful definitions. Intensity is actually energy transmitted per unit time per unit area. To have energy per unit time we use power, so it is power over area. How much power falls on unit area. Intensity is proportional to amplitude squared, which means that amplitude is proportional to square root of intensity. And for spherical waves from a point, as we can see, intensity is inversely proportional to distance squared. Or, because we have proportionality, we can use some constant k. More exactly, it is power divided by area of sphere. Mixed formula. Some constant, and from here we see that intensity is proportional to square of amplitude and inversely proportional to square of distance from source. Wave behavior. When wave passes from media 1 into media 2, it changes direction. We have angle of incident, angle of refraction, absolute refractive index of media 1 and 2, and here we have two equations actually. Also you should know about double slit experiment. S is distance between bright or dark fringes, lambda wavelength, d distance between slits, capital D distance from slits to the screen. Later on I will show you the picture. Constructive interference takes place when path difference is n lambda, destructive when path difference is n plus half times lambda. Here we have pictures. So absolute refractive indexes, angles of incidence and refraction are with normal. So this is the ray. Normal is line perpendicular to the boundary. Refracted index, refracted ray, normal, right. So we can say that n1 over n2 is relative diffractive index from 1 into 2. Very strange name. Absolute diffractive index of materials can be found using the speed. So speed of light in vacuum divided the speed of light in the material. Refractive index of air and vacuum is about 1. All rest material has more than 1 refractive index. If one material is air or vacuum, then you have the following simple formulas. Refractive index equals sine theta over sine 2. For light escaping from material, vice versa. If light if we go into material in which light goes faster, it is possible that that wave will not go through. This is critical angle, so greater than critical angle, light will not go through. So formula for critical angle is 1 over n. Now double slit experiment. So to observe interference we should have coherent lights. For this we create special conditions. So we have slit in front of a bulb. As a result, the light entering slit A and B will be coherent. What happens next? I showed with red arrows path differences from slits to some point. If path difference is n lambda, the lights come in phase and we have constructive interference, they reinforce each other and we have bright fringes. But at some points beside, the path difference will be n plus half lambda, and here they will come light will come out of phase, so they kill each other, destructive interference, and we have bright fringes. The distance between these fringes, sometimes called fringe width, which I don't like, this name I don't like, is given in the booklet. So lambda d is distance, small d is distance between slits, capital D is distance to the screen, and s is this distance, either between bright fringes or between dark fringes. Order of fringes: central 0, then 1, 2, 1, 2. So if they ask you number of bright fringes, you should count central and you should count on the left and on the right. Standing waves, no equations in booklet. So standing waves can be observed in strings and pipes. They are a result of one way traveling and another way reflected. What you should remember: distance between two adjacent notes is half lambda. For strings, the lowest frequency, which is called first harmonic or fundamental mode, frequency is V over 2 lambda. Second harmonic so much, and formula for nth harmonic will be so much. In pipes, at open end we have antinode, at closed end we have node. In antinode we have maximum displacement, at node we have no movement. For pipes with closed end, this is the formula for frequency. For two open ends, this is the formula. Examples: strings. How to analyze strings? So here we have string fixed at two ends, so at two ends we have nodes. This is the length, at the same time it is half lambda. This you should remember. This is formula for wave. We substitute lambda in terms of L, we get first frequency, or first harmonic fundamental frequency. What about second harmonic? So where we should put note somewhere, actually in the middle. So if we put note in the middle, we're getting next harmonic. Here you are. So note in the middle, next harmonic. From note to note we have vibrations. Here we have antinote, and let us see what we have. Lambda 2, lambda 2, lambda equals L. Now another relation between L and lambda. As a result, frequency will be 2 times F1, and so on. So we put another note, then we'll have 1, 2, 3, 4 notes, symmetrical, etc. Pipes. Pipe with one closed end. So note will be at the closed end, antinote will be at the open end. Because it is note and antinote, distance will be lambda over 4, not lambda over 2, and lambda over 4 equals L. As a result, from wave equation we get formula for first harmonic. Second harmonic. So second harmonic we should put antinote somewhere, and everything should be symmetrical. So antinote here. As a result, note here, antinote, antinote. Lambda over 2 and lambda over 4 equals L. So lambda equals 4/3 L. We get second harmonic. It is formula 2n minus 1. If we continue, we'll understand it. Pipe with 2 open ends. 2 open ends. So actually here I didn't show another part. It doesn't matter. Okay, actually it's clear. So first harmonic, antinote, antinote, lambda over 2 equals L. Very the same as string. Now we put another note in between, 2 notes. Lambda over 4, lambda over 4, lambda over 4, lambda over 4, 4 times equals lambda. So the same as strings. So F2 will be 2 Fn, F1, etc. So we finished page 5.